Hello, everyone, and welcome into the Sido and the Kiddos podcast. This is Nathan, along with Rachel, and of course, Sido. We got some cool stuff coming your way today. We are talking about the Julia set. We're going to dive into a brief history of the Julia set, give you some prereq info, including about relating to the Mandelbrot set, and then we're going to show you some cool photos, some cool diagrams, and some cool math. I hope you guys enjoy it, and that you come away with some cool takeaways. All right, without further ado, here's Sido.
A brief history of Julia sets. Julia sets were founded by Gaston Julia, who was a French mathematician, and he published his work in 1918 at the age of 25 years old, which is pretty amazing because I don't know that many 25-year-old people who've been able to discover something like this. Obviously, at the time, there haven't been any computer graphics, so it's really remarkable that he can figure out something complex, like something on a complex plane like this. In 1977, Mandelbrot was a French mathematician, which we've already studied about, and he basically popularized, emphasized on Gaston Julia's work, and kind of that's where the whole process has started on Julia sets.
Okay, so to understand what we will be talking about in this podcast, let's recall our RWR3, the video about the logistic map. In this video, we learned that the Mandelbrot set is arguably the most famous fractal, and that the bifurcation diagram is actually part of this set. It's based on the function z squared plus c, where you pick a number c in the complex plane, and because we are interested in the behavior of this equation, you start at z equals 0 and iterate it again and again. We learned that if it blows up to infinity, C is not part of the set, but if C stays finite after unlimited iterations, it is part of the Mandelbrot set. So the bifurcation is actually part of this set, which shows that the numbers in the main cardioid end up stabilizing onto a single constant value. In the main bulb, they oscillate back and forth between 2 values, and in the other bulb, they oscillate between 4 values, then 8, 16, 32, etc., etc. Then the chaotic part is in the needle, where the set gets thin.
So with that, here is the map of the Julia set. We're going to work with an f function such that c, the set of complex numbers, is mapped back onto c, where the function f is f of z equals z squared plus c. And to iterate this, we're going to do an iterative process to find all these points and whether or not they are in the Julia set. You pick a point c in the complex numbers, so you can choose any number such that it satisfies a plus bi. Even if you can choose b to be 0, so it's just a real number as well. Then you choose z naught. So you start with that point c, and then you choose a different z naught to be your first point. Then you find f of z naught to make a z1, f of z1, b z2, and you repeat that on and on and on. And so you see if starting from that z naught, whether or not that function remains bounded or not. So it could blow up. It might blow up and go into infinity, or it might not. So we repeat this for different z naughts. So after we choose one z naught, we'll choose a different z naught on that same c. We'll choose a different z naught, and so on and so on. So here I got a couple examples for you guys. We have f of z equals z squared plus c, where c equals negative 1 plus 0i. And like I said earlier, you can choose b to be 0. So that's what we did for this one. So we start with a z naught, and then we iterate it. We see that it was 0. See that f of 0 goes to negative 1, and so on and so forth. And we notice that this converges to a 2 cycle. Pretty interesting, right? And then we have a different z naught. Z naught is equal to 1/2. And then we iterate this a few times. And so I only put the first few iterations down. But if you go on and on and on, if you just do this on the calculator, you notice that for an infinite amount of cycles, or for an infinite amount of iterations, they eventually approach 2 cycle of 0, negative 1, which again is pretty common. It's common and pretty interesting. And yeah, so we're going to see some more about that.
What we are talking about here are filled Julia sets. One really important property of these is that they are bounded. If you have a function z of I, which is less than or equal to a bound that exists in the complex set of numbers for all i's in the natural set, then the function is bounded at z naught, and we fill it in on the graph. If not, we just leave it empty. In the example of the airplane Julia set, c is equal to about negative 1.75488. One example of Julia sets is called the basilica. A filled Julia set for function z squared minus 1, so c equals negative 1, is called the basilica because of its resemblance to St. Peter's Basilica. It is also known as the San Marco fractal. Orbits of points in the interior of the filled Julia set are attracted to the 2 cycle, while orbits of points outside escape to infinity.
So this example right here is probably my favorite. I'm not exactly sure how it's pronounced. I want to go with the Dowdy Rabbit, but Dave will just let us know how it's actually pronounced. I'll just call it the rabbit. So this is a fractal-like figure generated from a Julia set such that we have C equals negative 0.123 plus 745i. You know, it's crazy to me how they come up with these numbers. It's cool stuff, though, and this guy is, it's just cool, man. I don't know.
So one of the examples I like to talk about is the dragon one, and it's part of the quadratic family of Julia sets, which really just basically means that you have a function of z and is equal to z squared plus c, which is going to be a complex number, and c is approximately 0.28 plus 0.53i, which is imaginary, and that is an example of what the dragon work looks like.
There are 2 types of Julia sets, connected Julia sets and disconnected Julia sets. So the connected Julia sets are called Fatou sets, while the completely disconnected sets are called Cantor sets, and they both depend on the value of C. We say that a filled Julia set J is connected if it has no separating curves or a path which all the points relate to each other. And we say that it's disconnected if it has at least one separating curve. Disconnected Julia sets are often referred to as dust points on the plane where the points are spread out. There is also a really easy way to tell which of these possibilities occurs for a specific parameter value. When the point 0 escapes to infinity, then the Julia set is a Cantor set. But if 0 stays bounded under iteration of the map for all time, then the Julia set must be connected.
So the reason we talked about the Mandelbrot set at the beginning of this video to reflect on what it was and what it meant is to actually show that it is directly related to Julia sets, to the variety of Julia sets that we have. So the Mandelbrot set M is actually calculated as the subset of the complex plane where the C exists on C, the complex plane, such that the filled Julia set for Z squared plus C is connected. So all those cool examples we did, the basilica, the rabbit, the dragon, all that stuff, that C is plotted as black on this Mandelbrot set. If that C creates a Julia set that is connected, then that point is on the Mandelbrot set. It's really cool stuff. So all that red you see out there, those are disconnected Julia sets. And we're going to show you a little bit more on the next slide. Alright, so here is our Mandelbrot set, and we've got with it a few of the Julia sets that are reflected on that C. So it does look like, I know at first it looks like they're zooming in onto that point and showing that that's where the Julia set is, but that's not actually what's happening. What's happening is the C that correlates with exactly that point is what creates that Julia set. So, for example, we have the dragon up here in the top pretty much. So that C value that is plotted right there on the Mandelbrot set, that C is what creates the Julia set right there. And it's really cool. We've also got a nice animated video here that shows it, if I can pull it up real quick. Alright guys, so this is the link that I was talking about in our slide right there. It is a visual demonstration of what happens at various points in C compared to the Mandelbrot set. So right in the middle here, that's our Mandelbrot set, and then around it we can see all the Julia sets. So if we look outside of the black, here are all our disconnected Mandelbrot sets. Doesn't look like much right now, but the closer we get actually, the better and cooler these images look. So I'm just going to go around the Mandelbrot set real quick, showing you some of the cool disconnected Julia sets that we get at various C's. So here we go. Look like ninja blades. This one's a pretty cool one. This one looks familiar. I don't know if you guys remember. Alright, and then once we actually hit the Mandelbrot set, we see all the connected Julia sets that come up. So, and there you have it right as you hit it. Just to show you what difference is. And then I'm just going to take you guys through all of the Mandelbrot set. So the bulbs are probably my favorite parts, but we'll touch on all of it. So Here we go. Here's 0, pretty much. Forms a nice sphere. And we're just going to go through a bunch of it. Show you all the really cool images that come out of this. So that's the main bulb. And then if we go down to some of the secondary bulbs, you get some even cooler images, I think. So I'll just take you through that a little bit. Now remember, this is all for the various values of C. So wherever my mouse is for that value of C, such that the Julia set is closed, and this is the Julia set that it produces. So some really aesthetically pleasing and beautiful images here. If we keep going, I'll just go through the rest. This one's probably my favorite. Where if I can get it to curve. Nope, missed it. No, look at that. So cool. Right there, that one's my favorite. And we'll just go through the rest. So produce some stunning images. All right, and I'll send this link to Dave as well as posting it wherever other places it needs to go, so you guys can take a look at some of the stuff yourself if you're still interested. They have some interesting links on the site as well if you want to check that out as well. So there we go. All right, guys, and that pretty much covers all we're going to do today with the Julia set and the Mandelbrot set. I hope you guys really enjoyed this video. I can tell you I really enjoyed making it, and I really enjoyed some of the stuff that we covered today. A lot of it was just fascinating, incredible stuff. And we are just scratching the surface for some of the stuff here. There's a lot more to both the Mandelbrot set as well as all of the Julia sets. And there's some really cool stuff out there about this stuff. If you guys want to go and check it out, I would highly recommend it. If you have any questions, please feel free to reach out to me, Rachel, or Sido of Sido and the Kiddos. And I'm going to let Rachel take us out of here. So thank you guys for listening, and here, without further ado.
To wrap it up, we have a few questions to ask. In your own words, what is a Julia set? What is the relationship between Julia sets and the Mandelbrot set? Based on the examples provided, what Julia set example did you find interesting and why? We hope you enjoyed our podcast, and if you're interested in what we talked about, feel free to check out our resources.